This video is about a concept that's very important, especially in calculus, and it's called limits. And the way this works, one example, is if you have a sequence of numbers like 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot dot dot. Now if I made a function out of it, where I said like f of 1 is equal to 1/2, that's like the first term of this sequence, and f of 2 is the sum of the first two, so that would be 3/4, and f of 3 would be the sum of the first three, which is 7/8. It's getting closer and closer to the number 1, and the way we say that is we would say the limit of f of x, and now down here we say as x approaches infinity equals 1. That's a way of describing what's happening here. It's getting closer and closer to the number 1. It's not getting closer and closer to some other number. Here is a graph of a rational function, and when we describe, like, there's a horizontal asymptote here at y equals 3, one way of describing what's going on in this graph, which is really also describing some properties of this function, can be described using this limit notation. So saying there's an asymptote here, a horizontal asymptote, also says that the limit as x approaches infinity of f of x equals 3. Meaning here, this line, this curve is getting closer and closer to the number 3. It's also true, we have this branch on the left, that the limit as x goes to negative infinity of f of x also equals 3. Now, two other limits that seem relevant is what happens as I get close to this x equals 4. So the limit as x approaches 4, and now I'm going to put a funny thing here, a little plus sign after the 4. That means the limit as x approaches 4 from the right. In other words, here I am a little bit to the right of 4. I'm getting closer and closer, and it's getting higher and higher up. Fourth question, though, which does not have the same answer, even though it looks like almost the same question. This little minus doesn't mean negative 4. It means approaching 4 from the left. So if I'm approaching 4 from the left, and I know nothing about this thing on the right-hand side, it seems like the function is going towards negative infinity. Here's the graph of a different function. It doesn't have any asymptotes on it, but I could say that the limit of g of x as x approaches infinity is infinity, because it's just going up and up to the right, whereas the limit as x approaches negative infinity of g of x equals negative infinity, because it's going down like that. We don't put a little plus or a minus here, because if I'm going to infinity, I really have to be going from the left, and if I'm doing negative infinity, I have to be going from the right. Now over here, I would say the limit as x approaches 1 from the negative side would be of f of x, g of x, sorry, would equal 3, because it seems to be getting closer and closer to 3. It actually achieves 3 at 1. Whereas if I was going 1 from the right of g of x, if I'm on this curve going this way, as far as I know, it would be going to 5. So that's how to read limits off of graphs, especially graphs that have these discontinuities. Now, even if you don't have the graph of the function, there are times that you can find certain limits. An example of it is something like this, f of x equals 5. So that, I mean, we know that the graph is a horizontal line, but even if we didn't know it, I'm going to stick for now with limits as x goes to infinity. If the function is a constant, the limit's going to be a constant also. It's also true, this function, if I go to negative infinity. So that's, if it's a constant, that's one that we just kind of is common sense. But what if it's not a constant? If it's a polynomial function, you know, x squared or x cubed, something like that, in that case, f of x, oops, did I write limit here? Yeah. In that case, the limit of f of x as x goes to infinity will be infinity. And the limit of f of x as x goes to negative infinity actually is going to depend on whether our exponent is odd or even. So let's just stick with x to the first. Because that one's an odd exponent, it's going to be negative infinity. But if this was an even power, it would be positive infinity, because negative to an even power is positive. If we have a function that has a constant on top and a variable expression in the denominator, then f of x, the limit of f of x as x goes to infinity, that will be 0, because the denominator is getting bigger and bigger and the numerator is staying constant. If you have variables in both the numerator and the denominator, you can't just plug infinity into both, because you get infinity over infinity. But if you first reduce the fraction, it turns into this case, so it will be 0. Here's another one. If I put infinity in place of x, I'll get infinity over infinity. Well, what's that? Is that just 1? Well, if we cancel the x squareds, it turns into the first case. If I have a complicated numerator like this, we could actually take our, and again we want to know what's the limit as x approaches infinity of f of x. What you can do is you can split up and write it, sort of undo the addition of fractions, so you have all these fractions with common denominators. And the limit, this isn't true for all math things, but it's true for this. The sum of all these limits will also be the limit of the sum. But these ones individually, well, this one becomes 0 because it's a constant over a variable expression. This one becomes 0 because after I cancel it out, it becomes a constant over a variable. This one also becomes 0 because after I cancel out, it becomes a constant over a variable expression. But this last one doesn't. It turns into 4 over 2, which is just 2. And maybe this will remind you from last semester, where we would try to find the horizontal asymptote, and we would kind of ignore everything except for the biggest powers, and if they were equal, then we would just take the ratio of the two coefficients. Whereas if this was a smaller degree, then we would say that it was a horizontal asymptote at y equals 0. That's because we can kind of ignore this other stuff, and we can cancel out this x with that x, and we get a constant over a variable expression. And if this top exponent, and if this top exponent were bigger, if this was a 3 up here, we would say that it doesn't have the horizontal asymptote in this case. But that's because if we cancel out the x squared and we get 2x on top, we have the numerator, the denominator has constant, and the numerator has a variable, so then that's just a fancy way of saying the limit as x approaches infinity of f of x equals infinity. For this one, it was the limit as x approaches infinity of f of x equals 0. And this one, the limit as x approaches infinity of f of x equals 2/3. So it kind of agrees with what we did last semester when we were finding horizontal asymptotes, but it's a little bit more formal, and there doesn't have to be a graph for these limits. These limits are true whether or not anyone ever invented the idea of graphing or horizontal asymptotes. Okay, so that's going to do it for the first day of limits. More coming in the next lesson.